Hi, I'm Junaid Kaan, and I'm an assistant professor at Western Washington University, up, I think, 100 miles up from here, between here and Vancouver, BC. And this is a work that I've started with Kaan Ozbay, who is the director of C2 Smart Center at NYU. I was there as a postdoc, and this is a few years ago we started this, exploring blockchain for securing or kind of establishing trust in mobility data. So it's a continuation of our work. I think the work is called floating, and when we add the security flavor to it, there was a little, one problem led to the another one, and then we had to find a solution for the security aspect of things. So this is part of that work I'll be talking about today. Just a brief overview of the whole thing. So the main problem here we have is CAVs, or what we call connected and autonomous vehicles. The connectivity part needs to be explored more. So it means that they can talk to other vehicles, they can talk to roadside units, they can talk to pedestrians, anything that has a smart device that uses mobility data, or it can be logged. The biggest application we are looking forward is really autonomous vehicles talking to each other, sharing data, sharing trajectory data to safely navigate around each other. So having said that, if we imagine such vehicles or devices sharing data with each other to make navigation decisions, anything that can be a little bit malicious or faultious in terms of their data that they share can be deadly, especially for vulnerable users. So that are pedestrians, e-bikes or e-scooters that are more prone to accidents, or there are more fatalities if they are in an accident. So it's critical to trust the data that comes from those devices. On top of that, we really have a privacy and security problem. We can have an oracle or a centralized database that can take care of things, but then that will be a central or a single point of failure. So something that's robust, that lives on the road near to the devices, more often than an edge network. At the same time, we need to establish the trust model for those vehicles or the devices that can navigate around each other. So again, just identifying key shortcomings. If we go up with a centralized model, we'll run into a single point of failure. Attackers target big servers, big data leaks. I keep receiving emails that somebody's data got breached and my information went where, we don't know. So that's the thing. And then if we take it to the distributed approach, there are a lot of challenges. One of them is really, it's distributed. The resources are not that much. So it's slow processing, a lot of overhead, a lot of computational challenges for those devices. I mean, vehicles can take it, but not yet. I mean, you can put powerful GPUs and stuff, but then that would add more. If we are going towards e-vehicles, then we'll start counting how much charge are we consuming with all those extra stuff that we'd want to do. And security is usually after safety. And then to blend in this trade-off, we started with this approach. We leveraged federated learning, which is a way of distributed machine learning, primarily proposed for having privacy and having data on the devices so that they don't have to share it with some centralized server that kind of can be target of any breach. And then, again, the point that the data should stay on the roads near the vehicle. You reduce a lot on the communication overhead if you were to use any 5G or any of the networks that we have paid subscriptions for usually. And then on top of that, we kind of brought this SMPC, secure multi-party computation concept to vehicular network with a lot of challenges. I'll be honest, we've been struggling with implementing SMPC. So we took a very straightforward approach to just start with something really lightweight as a function. And just an addition function can sometimes be really easy to solve. And anything that's adds complexity as a function would definitely make this problem more complicated. And then what we've used is blockchain. So we kind of explored this for our saving or storing of records. It's that for gradual trust establishment. So the more you kind of get your data validated, or the more trust you establish over time, the more we can rely on you. And the model, I mean, that we use is really a consensus-based approach. So you have a bunch of nodes in a neighborhood that can validate each other's trajectories or whatever data they wanted to validate, and then they would endorse each other based off of whatever ground truth that they used. It could be the distances between them. It could be some side information like the weather or something else. So we've been exploring on these fronts and trying to bring up something that is scalable, that's lightweight, and then is also solving the problem at hand. So a straightforward model, it's just a bunch of nodes communicating with each other through wireless communication, technology independent, so it could be CV2X. We started working with CV2X now, as the US DOT is kind of leaning towards the technology. And then some trajectory data are being generated. So it's a time-stamped location information. They share it with each other in real time. We would focus more on the integrity attack. So we would have a network already established. So anybody who's talking to each other already is part of a blockchain network, which is a permission blockchain, if anybody is familiar with the concept. And then we let them run a consensus mechanism to validate each other's trajectories. And then if they are valid, they just get endorsed. And the information is stored on the chain. We have multiple flavors to the work, so I won't go into the details, but yeah. For this specific one, we kind of let the nodes predict what the, so if let's say I'm a connected vehicle and I share with you my intended trajectory for the next 10 seconds, and then what the other vehicle would do is they would just compare the trajectories, and then they would predict what the intended trajectory, the trajectory would look like for this specific vehicle using ML models, vision-based. We've seen examples of vision-based. Any technology, again, it's technology independent. And if that predicted trajectory matches with a certain threshold to whatever the vehicle has shared, you kind of build that trust over time. So that's the base for it. But then again, it's as simple as it can get, and you can add more complexity, but that would add to the time delays or the computation that the device has to do for validation. And for the prediction, we've gone through this federated learning approach, but we kind of broke it up to verified federated learning. So it's basically the model updates. As in any federated learning, you have a set of, you have a loss function, the local loss function, and then you have a global loss function. What you try to do is optimize the local loss function using the information from other peers that are optimizing collectively a global loss function, and every node regularly gets an update on the global loss from the global loss function to the local one. What we did is for each node we kind of split the loss function using SMPC into some secret shares, and then we will share, they will share with each other those chunks of the loss function, and then they will run some function on it, as simple as an addition function, and then we'll recompute what the values would be without knowing the exact value. So I have a very basic toy example here for an addition-based sum, like just they have this number, each one could generate three, like let's say a node 1 would generate value of 0, node 2 would have a value of 5.5, and then node 3 has a value of 4.5. The values all sum up to 10. They would keep one part of it, and the two others would be distributed among the other nodes. And then when they sum the values, each one of them, the combined sum of all the values for each chunk would be the exact value of the function that they're supposed to calculate. Again, it's a very basic example here, but this thing could be scaled up for any function. But with the caveat of not being too complex, because the more complex function they are asked to compute, the more resources we are consuming. So here's a high-level overview of the consensus algorithm. We just have some nodes that are, a node has a trajectory. It exchanges with nearby nodes within communication, and be that any technology. And then you as a node, when you receive it, you look at what has been shared, predict what that trajectory for that particular node would look like. If there is a difference less than some certain threshold, you would endorse it, store this information on a chain. we use IPFS, but I mean any distributed ledger or any storage can be used for the endorsement or the trustworthiness. For the consensus model, we are having a very straightforward majority rule. So if in a vicinity of each other, 51% of the nodes agree on the truthfulness of a node, we can count that node as trustable or kind of endorse it. We evaluated this on a simulated data set from, kind of initiated from the connected vehicles pilot project a couple of years ago. And we've used multiple simulation tools, so Sumo generating traffic, and then NS3 for simulating wireless communication and all the network. We have a scenario where we have a 1.6 mile stretch on Flatbush Avenue in Brooklyn as an example. The models for prediction, we've compared multiple. So we started off with simple and then moved on to little complicated, like transformer-based models. And I'll show you that the complicated one doesn't help much. I mean, they look great on paper, but they add complexity to the solution. So if you look at flops, or if you look at, so flops is floating operations per second. In terms of computational cost, they are heavy, but if simple RNN or an LSTM would, or GRU would do the job. Since we're dealing with trajectory data, that we don't need really big guns for solving this problem. Because we are getting acceptable accuracy and mean absolute error. So again, the outcome is really lightweight models for prediction, and then some stats on delays with the verifiable model. We kind of end up with it's actually the federated model that's kind of reducing all the time. That was usually exponential, and it just reduced to an optimal time that they're taking for training. We did up to 100 nodes. It's just a little challenging to measure for more nodes, but it does scale slowly. And then for overhead, we've also looked at the number of messages with different message sizes. Again, it could be different applications. And we found out that we are still under control for our communication overhead with varying message sizes. Some tests we did with the percentage of nodes that are kind of generating fake data. Again, we simulated that with NS3, and we found out that it's actually robust enough to have, even with 50% attackers, we are able to successfully endorse 75% of the nodes. So to summarize, this is one of a continuation of our works. Again, the problems are really challenging in terms of its scalability, in terms of computational complexity. I mean, the more we add a complex function to SMPC, the more time it takes. I've recently looked at some results that shown we've used homomorphic encryption in one of our experiments, and it just explodes the time that it took. So it's kind of an ongoing problem. The same thing is with applying it in real test beds. So we're kind of looking forward to that. And then the goal is really to have it private, scalable, and robust. And we're moving there. And if, again, anybody is interested, we are open to collaboration. If you have data, if you have resources, happy to talk about it. Thank you.